KURINJI Senior Secondary School, CBSE, Namakkal.
Successful result producing school in state every year.
Administered by the Board of Directors with over 35 years of experience in the teaching field.
Special attention on art, craft, music, dance, silambam, yoga, skating and karate.
Focus on Hindi Sabha and Spell Bee Olympiad exams.
Smart class for effective and innovative learning and well-furnished library.
Solitary importance on sports and games in state and national level.
WhatsApp facilities to know activities of students and school inside the campus.
NEET, JEE, IIT coaching experts from Rajasthan and Andhra Pradesh along with our effective teachers.
Admission registration for classes LKG to +2.
KURINJI Educational Institution, Kavetipatti, Namakkal. Admission in progress. CBSE, KG to 12, contact 9025895176. Metric 6 to 12, contact 9344567484. For online admission, log on to www.kurinjischoolnkl.in.
In continuation to the last class, in this class we start to discuss the concept of shear modulus. Okay, shear modulus. After completion of that, we will discuss one example problem and then we will discuss bulk modulus. We already discussed Young's modulus of elasticity. Young's modulus of elasticity. So, what is elastic moduli and then what is Young's modulus of elasticity we discussed. Now, we are going to concentrate to discuss shear modulus. See this, okay? See this. The ratio of shearing stress to the corresponding shearing strain. The ratio of shearing stress to the corresponding shearing strain, right? Which is called as shear modulus. Shear modulus of the material and is represented by capital G. So it is what the definition I am saying. The ratio of shearing stress to the corresponding shearing strain is called the shear modulus of the material. Shear modulus of the material and is represented by capital G. And you know what is meant by shearing stress? That's what we already discussed in our previous classes. So when we were in a discussion regarding the different types of stress and different types of strain, so there we discussed what is shearing stress. Okay, ma? Shearing stress is nothing but the restoring force per unit area developed. The restoring force per unit area developed due to the applied tangential force. Due to the applied tangential force, which is called as shearing stress. So I will repeat once again. Shearing stress is the restoring force per unit area developed due to the applied tangential force. Due to the applied tangential force. The same here also we can experience. See the dotted lines and solid lines. When you are going to apply the force, what will happen? That is going to move from its actual position to some other extent. To some extent, that is what when the force is applied tangentially. When the force is applied tangentially. Okay. So shearing stress, that is sigma s divided by shearing strain. So obviously strain is nothing but the ratio. Strain is the ratio of change in dimension to the original dimension. When you go for mathematical treatment to derive the formula with notations, G is equal to F by A divided by delta x by L. Delta x by L. So here that is equal to F into L. F into L divided by A into delta x, because delta x by L is in the denominator. When it goes to the numerator, it will be like L by delta x. So F into L by A into delta x is the formula to calculate shear modulus. To calculate shear modulus. Okay. Shear modulus is also called the modulus of rigidity. One more name. Shear modulus is also called the modulus of rigidity. And one more thing, in our previous discussion, I think 3 classes before, when we were in a discussion about the tangential stress or shear stress, there we got a quantity of, that is trigonometric quantity of tan theta So when tan theta, you can take it as approximately equal to theta. When theta is small, tan theta is approximately equal to theta. With that consideration, we can write G is equal to F by A divided by theta. That is equal to F by A into theta. F by A into theta. Okay. Next, the shearing stress sigma S can also be expressed from this. From this, the shearing stress sigma S can also be represented or expressed as sigma S is equal to G into theta. Sigma S is equal to G into theta. Why? Because see, if you take F by A and take this theta to that side, then G into theta, no. So F by A is what? Shearing stress. So shearing stress is equal to G into theta. Also we can write. And SI unit of shear modulus, it is Newton per meter square or Pascal. Why? Strain has no unit, no. Strain has no unit and no dimensional formula. That is the reason the unit and dimensional formula of stress as same as shear modulus. Okay, I can repeat once again. Shear modulus, the unit and dimensional formula of shear modulus is same as shearing stress, because shearing strain has no unit and no dimensional formula. It is like a pure number. Next, the shear moduli of a few common materials. The shear moduli of few common material we have given in the table. That is what, this is the table. Here you can see. So from this table you can observe shear modulus is generally less than Young's modulus for most of the materials. Capital G is equal to Y by 3. For example, the same thing, whatever it may, for example, iron. Okay, so iron, you take the Young's modulus and you take the shear modulus. So it is almost 1 by 3rd of the Young's modulus. That's why he can say G is equal to Y by 3. And one more observation, here we have a list of values of shear moduli for different materials. For aluminum 25, for brass 36, for copper 42, and for glass 23, iron 70, lead 5.6, nickel 77, steel 84, tungsten 150, wood 10. Out of all these things, which has highest value of shear moduli, which is tungsten, no? That is the value of 150. 150 is the shear moduli of tungsten. And what is the least value? Here, least value is 10, no? So that is for wood. So based on these two. Otherwise, you can't able to imagine, means you just take iron and wood, because the usual things, no, generally you can experience and we observe and we touch. So iron is 70 and wood is 10. So shear moduli of iron is more than the shear modulus of wood. Like that, these are all we are using in our daily life. Aluminium for high tension wires, to make high tension wires. For brass, olden days we had vessels also. And then copper, right, copper vessels, and glass we are using. Iron also we are using, lead, nickel, and steel, tungsten. Okay, tungsten we are using to make filaments of the bulbs, no, right, 60 watt, 40 watt bulbs are there, no, in our house. So there we are using tungsten to make filament. So for filament, that is what shear moduli is, maybe the one of the reasons. So why we are using a material tungsten to make filaments, means the reason is the shear moduli is high. The shear moduli is high. Right. Next, come to this point again. That is what I already told you. For most of the materials, G is equal to Y by 3. So this is the relation which is very important. He is relating. That is what the shear moduli to the Young's moduli. So G is equal to Y by 3. Next, here we have an example problem. Now we will go through the example problem. A square lead slab of side 50 centimeters, you can see here, of side 50 centimeters and thickness 10 centimeters. Thickness 10 centimeter is subject to a shearing force. Is subject to a shearing force on its narrow face, on its narrow face, in the bracket I mentioned there, to a shearing force on its narrow face of 9.0 into 10 to the power of 4, 9.0 into 10 to the power of 4 newtons, full stop. The lower edge is riveted to the floor. The lower edge is riveted to the floor, full stop. How much will the upper edge be displaced? How much will the upper edge will be displaced? Right, ma? It's a nice question to understand the shear moduli or shear modulus. Okay. See, they have given a square lead slab of side 50 centimeters and thickness 10 centimeters. Is subject to a shearing force. Is subject to a shearing force on its narrow face of 9.0 into 10 to the power of 4 newtons. So this is the force we are applying. This is the force we are going to apply onto the square lead slab. The lower edge is riveted on the floor, to the floor, right? How much will the upper edge be displaced? Okay, see the answer. The lead slab is fixed. The lead slab is fixed and the force is applied parallel to the narrow face. Parallel to the narrow face as shown in the figure. This is what the figure now. The area of the face parallel to which the force is applied. The area of the face parallel to which this force is applied is A is equal to, because one side is 50 centimeters, another side is 10 centimeters. So 50 centimeters into 10 centimeters, no, which will give us area. So 50 centimeters into 10 centimeters means, 50 centimeters means you can write it as 0.5 meters and 10 centimeters means you can write it as 0.1 meter. So 0.5 meters into 0.1 meter means, which is 0.05 meter square, 0.05 meter square or square meter. Therefore, the stress applied is, this is the area, and you know what is the formula for stress? Force by area, no? Right. Therefore, the stress applied is 9.4 into 10 to the power of 4 newtons. It is the given value. 9.4 into 10 to the power of 4. Okay. That is the given value. And now divided by 0.05 square meter. 0.05 square meter. So, which will give us 1.80. Which will give us 1.80 into 10 to the power of 6. Okay, see here, it is 9.0, 9. The given value, right? Anyhow, the value is not a matter now, obviously, because the procedure is important regarding one physics problem. I told you many times, okay? Right, anyhow, the value they have given 9.0 into 10 to the power of 4 newtons divided by 0.05. So, which will give us, see, it is 5 into 10 to the power of minus 2, no? So, 10 to the power of minus 2 goes to the numerator, means it will be 10 to the power of plus 2. So, 9 by 5 means 1.8. So, it is 1.80 into 10 to the power of 6 Newton per meter square. Newton per meter square. Next, we know that shearing strain. We know that shearing strain is equal to delta x by L. Delta x by L is equal to stress divided by stress divided by capital G. You can see here, delta x by L is equal to stress divided by capital G. So, when it is stress divided by capital G, you just substitute the value of stress and capital G by writing delta x as a subject. So, delta x, if you write delta x as a subject, then what will be there? Stress into capital L by capital G, that is equal to 1.8 into 10 to the power of 6 Newton per meter square into 0.5 divided by 5.6 into 10 to the power of 9. 5.6 into 10 to the power of 9 Newton per meter square. Okay. That is equal to 1.6 into 10 to the power of minus 4. See here, it is 5 into 10 to the power of minus 1. No? 10 to the power of 6, 10 to the power of minus 1, 10 to the power of 9. So, here it is 10 to the power of 5 and it is 10 to the power of 9. It is 10 to the power of 5, it will be 10 to the power of 9. Then finally what is the answer we are going to get here? Totally we are going to get 1.6 into 10 to the power of minus 4. 1.6 into 10 to the power of minus 4 meter. So minus 4 meter means obviously which is equal to 0.16 millimeter. 0.16 millimeter, no, that is because what is the value of L they have given? Stress into L by capital G. Stress is okay, we calculated, which is 1.8 into 10 to the power of 6 Newton per meter square, but into capital L, that is what, 0.5 meter, no, 0.5 meter. So when it is 0.5 meter, here it is 0.5 meter, it is 5.6 into 10 to the power of 9 Newton per meter square. So what is this? It is capital G. It is capital G. Capital G for what? Capital G for what, right? Capital G based on that given value. Right, here G value is according to the table. Here you can get it as 5.6 into 10 to the power of 9. That is for lead, because it is what, square lead slab, no, that's why here he has taken 5.6 into 10 to the power of 9. That is equal to 1.6 into 10 to the power of minus 4. If you convert into millimeters, which will give us 0.16 millimeter, 1.6 into 10 to the power of minus 4 meter. In place of meter, you just write, right, in place of meter, you just write 1000 millimeter, because 1 meter is equal to 1000 millimeters, no. So 1 meter is equal to actually 100 centimeters. 1 centimeter is equal to 10 millimeter, no. That's why you can say, that totally 1.6 into 10 to the power of minus 4, 1.6 into 10 to the power of minus 4 meters is equal to 0.16 millimeter. Next, bulk modulus. Just now we discussed about shear modulus. Along with that, one example problem based on the calculation of shear modulus and as well as stress also. Stress, and then based on the shear modulus we discussed one example problem. Now we are going to discuss bulk modulus. See this. We already discussed, we have seen that when a body is submerged in a fluid, it undergoes a hydraulic stress equal in magnitude to the hydraulic pressure. For example, by taking a tub of water, you just drop a ball. Then what will happen? So the ball is going to float. That is because of hydraulic stress. So not only water and ball, in many cases, for example, even if you take a small dust particle, a piece of paper, which is floating in air, no, which is floating among air molecules, no. So air is a fluid. So that's why floating means not only for water, so it is also for air. Okay, that's why finally what I am saying is, when a body is submerged in a fluid, it undergoes a hydraulic stress. So this is equal, this hydraulic stress is equal in magnitude to the hydraulic pressure. This leads to the decrease in the volume of the body, thus producing a strain is called volume strain. This situation leads to the decrease in the volume of the body, thus producing a strain called volume strain. Here itself we can define one more physical quantity, that is what, bulk modulus. So bulk modulus is the ratio of hydraulic stress to the corresponding hydraulic strain. Bulk modulus is the ratio of hydraulic stress to the corresponding hydraulic strain. So that's why you can say B is equal to minus P divided by delta V by V. So this minus is attributed to numerator. You can also write like this: bulk modulus is equal to hydraulic stress by hydraulic strain. Mathematical formula: B is equal to minus P by delta V by V. There is a negative sign, no? So this negative sign indicates the fact that with an increase in pressure, decrease in volume occurs. With an increase in pressure, decrease in volume takes place. Okay, that's why B is always positive. B is always positive. And You can also say that, see here, if P is positive, delta V is negative. That only I am saying, no. Negative sign indicates the fact that with increase in pressure, decrease in volume occurs. That is, if P is positive, delta V is negative, full stop. Thus, for a system in equilibrium, the value of bulk modulus, B is always positive. To be the system in equilibrium, the value of bulk modulus B is always positive. SI unit of bulk modulus is Newton per meter square or Pascal. The bulk moduli of a few common materials, right? The bulk moduli of a few common materials, you can see from our textbook, that is what, for example, aluminium, the bulk modulus is 72, brass 61, copper 140, glass 37, iron 100, nickel 260, steel 160. Suppose if you take the liquids, water, it is 2.2, ethanol 0.9, carbon disulfide 1.56, glycerin 4.76, mercury 25. Suppose if you take gases, air at standard temperature pressure, it will be 1.0 into 10 to the power of minus 4. So whatever the values I told, this is all the order of 10 to the power of 9 Newton per meter square. Order of 10 to the power of 9 Newton per meter square. Suppose if you see all these things, regarding the solids, nickel has that is the highest value of bulk modulus, which is 260, and the least is 37, that is glass. If you take the liquids, mercury has highest value of bulk moduli, that is 25, and the least is 0.9, that is ethanol. Regarding the gases, they have given air, that is 1.0 into 10 to the power of minus 4. Okay, right. Now, see, the reciprocal of the bulk modulus is called compressibility and is denoted by K. One more quantity, that is what compressibility. So the reciprocal of the bulk modulus is called compressibility and is denoted by K. It is defined as the fractional change in volume. It is defined as the fractional change in volume per unit increase in pressure. It is defined as the fractional change in volume per unit increase in pressure. That is what you can write like this. K is equal to 1 by B, that is equal to minus 1 by delta P into delta V by V. Right? That is what you can write. You can also see this. See, just now I told you some of the for some of the solids and liquids and gases, I told you what are the values of bulk moduli. Okay. Generally, if you compare solids to liquids, right? So the bulk moduli for solids are much larger than for liquids, which are again much larger than the bulk modulus for gases. That's why you can say that the solids are least compressible. Whereas gases are most compressible. Solids are least compressible, whereas gases are most compressible, right? Gases are about 1 million times. Gases are about 1 million times more compressible than solids. You just imagine. Million means what? 10 lakhs. 1 million means 10 lakhs. So 10 lakh times gases are about 10 lakh times more compressible than solids. Okay, that is. And gases have large compressibilities which vary with pressure and temperature, which changes with pressure and temperature. The incompressibility of the solids is primarily due to the tight coupling. The incompressibility of the solids is primarily due to the tight coupling between the neighboring atoms. Okay, the molecules in liquids are also bound with their neighbors but not as strong as in liquids. The molecule in liquids are also bound with their neighbors, but not as strong as in solids. Right, full stop. Molecules in gases are very poorly coupled to their neighbors because they are very free now. You know, just already we had information about solids, liquids and gases in physics and in chemistry also, right? So that he can say molecules in gases are very poorly coupled to their neighbors. Okay, ma? Right. That is what we discussed in this class. So in this class we discussed shear modulus and one example based on the shear modulus. Afterwards we came to discuss bulk modulus. Okay, right. So in the next class we will continue with the next continuation example problem, that is example 9.5. Thank you.